In this screencast, I'm going to talk about how to use computers, and I guess a person could use a calculator as well, to figure out, mathematically speaking, and maybe graphically speaking, what shape we might be looking at for a given set of data. So here, I'm alluding to an experiment where we have a constant force on a cart, but we add more and more blocks of mass, changing the mass of the cart. And I wonder what this shape is. The first method, out of two methods that I'm going to talk about, involves just asking a computer to figure it out for you. So if I use Microsoft Excel to make this plot, and there's another screencast in which I explain how to do that, I can add a trend line. And when I'm within the menu of what type of trend line to add, I can choose whether I want it to be a line or a logarithmic function or a power function, including a square root or including x to the negative 1. I can have a polynomial function of any order that I choose. Y equals, I guess a third order polynomial would be x cubed plus some coefficient times x squared plus some coefficient times x plus some coefficient times a constant, or some coefficient. Let's say I want to make a guess. I bet that's a quadratic function. Well, when I choose a power function here in Excel for the particular data that I'm analyzing in this slide, I see that it gives me this result with an r squared value of 0.98777. And an r squared value, it basically tells you how good a fit a trend line is to the data that you've given. So you might imagine that maybe we have a trend line that just perfectly hits all of the data points. That would be a really good fit. That would be an r squared value close to 1. R and r squared are terms that we use from statistics. You might also imagine that purely random data would not fit a quadratic curve very well. And so a computer would say that the r squared value is close to 0 in that case if the fit of the trend line with the data points is very bad. I might guess that maybe this decreasing trend of data is 1 minus a square root function or something like that. A square root function increases, but some number minus a square root function is another, is a excuse me, a decreasing curvy shape like that. It's tricky in Excel because actually when you ask it to fit a power function, it chooses among all of the different powers. It chooses, you can't say, I want you to fit a parabola to this. It will choose the exponent it thinks goes best, whether that's squared for a quadratic or to the 0.5 for a square root function. Don't worry too much about this. I do want to show you how, I guess I do want to show you that when you fit a power function to this data, Excel, when you get it to display the equation, it thinks that we're looking at some number times x to the negative 0.946. So this all by way of saying sometimes you can just make Excel give you a line of best fit or some other curve of best fit. But if you're trying to test out these guesses, Excel is not the best tool to do that. Here is a good tool to do that. It is by using the method of linearization. And it involves, well, okay, so I guess let's say these are our three guesses again. Maybe this shape of data, maybe the real relationship between our cart's acceleration and its mass is an inversely proportional relationship, that the acceleration is some constant times the inverse of mass plus some other constant. Or maybe, really the relationship is that this is a parabola, that the acceleration is equal to some constant times the square of the mass plus another constant. Maybe that's not such a good idea because a parabola would suggest that the acceleration value would rise and rise for even greater mass, but it's a guess that we could have and that we will use a mathematical technique to check. Or maybe we think maybe this is 1 minus that square root function, and that might not be a great guess either because a square root function continues forever and ever to increase. So I guess 1 minus a square root function would continue to decrease. So at a big enough mass, it would suggest a negative acceleration, which isn't, that wouldn't really make physical sense. But we'll talk mathematically about how to check these guesses. Well, here's a fact. Y equals mx plus b. In other words, if some y value really equals a constant times some other variable that I will call red box instead of x, plus c2, if this really is a true equation, then when you graph y versus red box, that graph is linear. This is just saying y equals mx plus b, except for the, I'm not using the letter x, I'm using red box. And the slope of that line is the first constant, and the y-intercept is the second. Well, let's check our first guess about the shape of this graph. Remember, our first graph was that the acceleration was related to the inverse of mass. Well, if it really is true, if the acceleration really is some constant times 1 divided by the mass plus some other constant, then the graph of the acceleration versus 1 divided by the mass should be linear. And maybe that's a weird thing. You've never seen a graph of acceleration versus 1 over mass before. But maybe I'll just call it red box, and I happen to be putting 1 divided by the mass into the red box, and this really is an okay thing to do. I'll make Excel give me a column of data representing 1 divided by the mass. My screencast about how to use Excel explains how to do that rather quickly. And so now let's see about this data table. Yeah, for the mass of 0.3 kilograms, the acceleration was 6.5 meters per second squared. 1 over the mass, 1 over 0.3 is 3.33333. And what are the units? It's really 1 divided by kilograms. So this is odd stuff. The thing that I actually have in this column and on this horizontal axis is the quantity of the inverse of the mass of the cart, and the units of that are 1 divided by kilograms. What are we doing again? We're checking the guess. Maybe this graph is a hyperbola. Maybe the acceleration is inversely related to the mass. Well, if that's true, then by this mathematical fact, this graph should be linear. Is this graph linear? Why, yes it is. Look at that r squared value for when I fit a line to this trend. A very good r squared value. Okay, well what does that mean? It means since this is a linear function, then it really is true that the acceleration is some constant times the thing on the horizontal axis, 1 divided by the mass, plus some other constant. And I actually have had Excel tell me the value of those constants. I've had it show the equation. That's something that you can do in the options for your graph. So is this it? Is A equal 1.91 times 1 over mass plus 0.09? Well, I don't think we're done because this equation doesn't work as far as units go. The units on the left are meters per second squared, so the units on the right need to be meters per second squared. I'm also prepared to drop this constant term because it's so close to 0. Look, that plus or minus 0.09 is a very small number compared to the actual values of the acceleration here. So I'm going to drop that last term. And I'm going to ask myself, well, what should the units of this 1.91 be? Well, the units of the left side, the units of acceleration are meters per second squared. And that's going to be equal to whatever units I'm about to put on the 1.91. I've indicated that with empty square brackets. Times whatever the units of this are, that's units of 1 divided by kilograms. In other words, the units that have to go in this bracket is kilogram meters per second squared. And you might be thinking, oh my gosh, what is a kilogram meter per second squared? We're actually going to end up having something interesting to say about it, but for now, you can just know that it's mathematically required to go right after this 1.91 in order for the units of the left to match the units of the right in our equation. This is an example of the specific numerical result for this data. So here's a data table and a graph of the data. Here is a linearized data table and a graph of the linearized relationship. And here is a correctly formatted specific numerical result. The acceleration for this lab group is 1.91 kilograms meters per second squared times 1 divided by mass. These m's are different, so they don't cancel. Here's meters, and there's mass in that denominator. So I'm pretty happy with this result because my r squared value was so good. But I wonder if maybe a parabola fits this data even better than a hyperbola. Let's check. Let's check guess 2, a parabola. Maybe the acceleration is really equal to some constant times the mass squared plus c2. Well, if that's true, then the graph of the acceleration versus m squared should be linear. So I've done it. I've made Excel give me a linearized data table, or I'm attempting to linearize the data. I display m squared and a. Now the thing that I'm graphing on the horizontal axis is the mass squared. That would be measured in kilograms squared. And if this is a true equation, then this graph should be a line. Is it a line? No, it's not very linear. Excel is saying r squared is equal to only 0.68. This is not a very good line. So this graph, this original relationship is not very parabolic. Guess 2 was not a good guess. And again, in my other screencast, I show you how to very rapidly make the m squared column. Well, maybe it's 1 minus a square root function. Let's try that. If this really is the mathematical relationship between a and m, if a really is equal to a constant times root m plus c2, then the graph of a versus the square root of m should be a line, should be linear. Well, let's get Excel to whip us up a nice graph of acceleration as a function of the square root of mass. If that shape really is 1 minus a square root function, then, if the original shape is 1 minus a square root function, this graph should be a line. Is it a line? It's not a very good line. R squared is only 0.89, so it's kind of linear, but it looks like guess 1 was the best, the inverse relationship.